Now let's look at an exponential function. First, let me give you what is the form of the function, which is called the exponential function. An exponential function is a function of the form of f of x equals a to the x. So x is in the power, where this a is positive, right? Positive real numbers, and a is not equal to 1. Otherwise, it's always be 1, right? It means nothing. So here, this is the exponential function. And here is some remark. This x, if a is positive and a is not equal to 1, this x, so what is the domain? The domain is all real numbers. All real numbers, which is from negative infinity to infinity. Okay, you can plug in any x values. 2, this a is called the base. Okay, a is a positive number and not equal to 1. So now let's look at some graphs. Okay, so f of x graphs of this function. So let's look at, for example, let's look at f of x equals 2x. Okay, so since we don't know the graphs, so we can just find some sample points, right? We can take this x, this is the f of x, right? So this is, if x takes to be 0, it would be 2 to the 0, which is equal to 1, right? So that means you must have a point, 0, 1 point. If x equals 1, then it would be 2 to the 1, which is 2. So you have the 1, 2 point. If you have negative 1, so this is 2 to the negative 1, which is 1/2. So you have negative 1, 1/2 point. Okay, of course you can give more points, but here I just use these 3 points. 1, 0, 1, 0, 1 is here, right? And 1, 2. So 1 is here, 2 is here. So this is this point, right? 1, 2 point. And negative 1 is here. And this is the 1/2 is here. So this is the point. Negative 1, 1/2. So we use some smooth curve. Then you can see that this is, okay, if you can find more points, you will notice that this y equals 0 is the horizontal asymptote. So now let's look at another example, which is f of x equals 1/2 to the x. Okay, so we still use some sample points. This is x, this is f of x, and then this is the point. So here is when x equals 0. So this is 1/2 to the 0, which is equal to 1. So it must go through the point 1, 0, 1 point. When x equals 1, so this is the 1/2 to the 1, which is 1/2, right? So this is the 1 and the 1/2. When x equals negative 1, so this is 1/2 to the negative 1, which is 2. So it must be negative 1, 2 point. So now let's locate these points. So 0, 1, right? And 1 and 1 half. 1 is here, 1 half is here, so this is 1 half. And negative 1, 2, this is negative 1, 2, so it would be here. So the graph will look like okay, so this is the graph for this function, and you will see that if you have more points, this horizontal asymptote is y equals 0, which is x-axis, right? So from both graphs, if the base is 2, then it will be increasing function. If the base is 1 half, it would be decreasing function. And these two graphs are also went through the same point, which is the 0, 1 point. In other words, y-intercept is always be 0, 1. There is no x-intercept. So now let's summarize the general case. So now let's look at, in general, f of x equals a to the x, where a is greater than 0 and a is not equal to 1. Okay, so for the first case, where a is positive, this is a is positive. A is greater than 1. Then we will look at another one, which is a is greater than 0, less than 1. We have two cases. For a greater than 1, in this example, this is 2 is greater than 1, so the graph should look like this one. Okay, so the graph would be an increasing function. Okay, it must go through the point 0, 1 point. So from here, from the graph, we notice that the domain is always being what? From negative infinity to infinity, which is the x values. Any x value you can take. Okay, and the range from the graph, this graph is above x-axis, and we never touch x-axis, so the range is 0 to positive infinity, right? This is this part, right? This is the range, all the y values. And we have the y-intercept. Y-intercept here, which is 0, 1. What about the x-intercept? There is no x-intercept. None. And we also have a horizontal asymptote. Which is y equals 0, or x-axis. And this function is increasing function. It is increasing function. So as x becomes larger, the y value becomes larger. Okay, so this is this case. For a is less than 1, which should have, this here is 1 half, which is less than 1, greater than 0. Okay, so it should be this curve. So that's it would be this one. And this point is still 0, 1 point, right? So the same thing, let's look at the domain. Domain is corresponding to all the x values, so it's from negative infinity to infinity. Range above x-axis but never touch x-axis, so it's from 0 to positive infinity. 0 have the parentheses. y-intercept. Y-intercept is still 0, 1, right? This point. And x-intercept, there's no, because it never touch x-axis. So there's no x-intercept. And the horizontal asymptote, still the same, which is y equals 0. And as x is increasing, y is decreasing. So this is a decreasing function. Decreasing function. Okay. So this is the summarize for the graph of f of x equals a to the x, the exponential function. So now let's look at the graph. We want to find the graph for this function f of x equals 3 to the x minus 2. So here you should be careful. 3x minus 2 is not the same as 3x minus 2. Okay? So many students will make this kind of mistake. The reason is they always subtract 2 on the x, but actually this is 3 to the x. Then the whole thing subtract 2. Okay, so here is the power exponent subtract 2 then, which is the power of the 3. Okay, so now let's look at this one. When we draw the graph, okay, the first thing is we need to know what is the basic function for this basic function or the parent function. Okay, so here is, which is y equals 3 to the x, right? Y equals 3 to the x. So this is this one. And you can sketch the graph. So this is y equals 3 to the x. Then we subtract 2, right? We subtract 2 to get y equals 3 to the x, then subtract 2. That means we will need to, because we subtract 2 on the whole value. So original subtract 2 from this one, right? The whole function from the whole function here, right? So we need to move down 2 units. Okay, move down 2 units. So this is the 0, 1 point. And if you move down 2 units, it becomes -1 minus 2, right? -1. So here is 0, -1. And the horizontal asymptote, which is from y equals 0 to move down 2 units, becomes y equals -2. So this is -2. So this is the horizontal asymptote. Then we draw the graph. Okay, so this is the graph for this function. So here y equals -2. This is the horizontal asymptote, right? So here is the horizontal asymptote is y equals 0. So we always start from the graph that we know. This is called the graph for the basic functions, okay? From this one, we can see that the domain doesn't change, right? The domain is still from -infinity to infinity. What about the range? The range. So you will see that the horizontal asymptote is negative, y equals -2. So the graph is always above -2, y equals negative. So it should be greater than -2 to positive infinity, right? So this is the range. Okay, so now let's look at another example. We still want to look at the graph for the function of -2 to the x plus 1. So here is the one thing, that -2 to the x plus 1 is not the same as -2 to the x plus 1. So they are different. So this one the left side is we multiply a -1 on this exponential function. And the right side is actually the base is -2, right? That is totally different. Okay, so again, for this one, we need to look at the parent function for this, well, the basic function, which is y equals 2 to the x, okay? 2 to the x, let's draw the graph for this one, 2 to the x. Goes through the point, 0, 1 point. We always use this point to locate our graph, right? The position of our graph. Okay, so what we should do next, in order to get this one, let's multiply a -1 to get y equals -2 to the x. Of course, you can look at 2 to the x plus 1 first. It doesn't matter which way you will go first. So here, I want to use this one. Okay. So you will see. We multiply a -1, so we flip this, reflect this curve along the x-axis, right? So here, this point, 0, 1 point becomes 0, -1 point. So the graph will look like this one. Okay, the graph will look like, we still have the horizontal asymptote y equals 0. Then the next one is, what we should do next? Next one is, from here, we add 1 on x. So it becomes x equals -2, x plus 1. So remember, if we add a number on x, right? We add a number on x, So we add 1 on x, so we will move the graph to the left by 1 unit, right? So we still need to look at some special points. So if you move to the left by 2 units from 0, 1, 0, -1, so you will get -1, -1, right? This point, this is the -1, this is -1. So you have this -1. So since we move the curve horizontally, so the y equals 0 is still the asymptote, right? So you will have y equals 0 is still the horizontal asymptote. So the graph will look like this one. The graph will look like this one. Okay. So this is the typical way we need to find the parent function, right? Which is the function we already know. Then we multiply by -2. We try to convert to be the final function. So we multiply step by step. We multiply by -1. So we flip. Then we add 1 on x. So we will move to the left, right? So now let's look at some properties. The properties for the exponential function. So the first one is a to the x times a to the y should be equal to a to the x plus y. Okay, so all these properties you should memorize, and many students will make mistake, right? 2. This is a to the x, then the whole thing raised to the power y. It's actually equal to a to the x times y, right? If you have 3, if you have a to the x divided by a to the y. Then it's equal to a to the x minus y. So we have some common mistakes. I have seen many times in the students' homework. So we have see, okay, so this is the one thing, a to the x times y. They say, okay, it's equal to a to the x times y. No, it's not equal to. Okay, so this one, y is multiplied on the whole a to the x, not on the exponent. And then we have a to the x plus a to the y. They say, okay, it's equal to a to the x plus y. No, you cannot combine a to the x and a to the y if the operation is addition or subtraction. Okay. So now let's look at another, the fourth property, which is used to solve some equations, okay, exponential equations, which is a to the x is equal to a to the y if and only if it's equivalent to say that x is equal to y. So this is called the one-to-one property, right? If this function, exponential function, equals another exponential function with the same base a, then the exponent, the input must be the same, right? The y values is the same, then the input is here, this is the input, right? This input must be the same. So this is called a one-to-one function. And from the graph, we also see obvious, right? Because the graph will looks like this increasing function, this is decreasing function. If you draw the horizontal line, right? It will intersect only at one point, so it's one-to-one function, right? So now let's look at some examples using this property to solve some exponential equations. Phi to the 1 minus 2x is equal to 125. Okay, we solve this one. In order to use this property, we needed to change the right side as phi to something, right? So, okay, so it's not hard. You will see that 125 is actually phi to the third. So this property tells you that if these two are the same, then the exponent must be the same, right? So it means 2x equals 3. So you will have negative 2x equals 2, x equals negative 1. So that is your solution. So this is the one example. Another example is 4 to the x squared. Okay, the power is x squared. And here is 8 to the x. So the first thing is you need to have the same base, right? To use this property 4. We need to have the same base, but the one is 4, the other one is 8. However, you will see that 4 is equal to 2 squared, right? So it's 2 squared then to the x squared is equal to 8. 8 is 2/3 of then to the x, right? So now we can use this property too, right? To simplify, it's equal to 2 to the 2x squared is equal to 2 to the 3x. Okay, so now we have the same base too. So we can use the property 4, right? So the exponent must be the same. So again, when you solve this kind of function, you cannot divide by x directly, because if you divide x, you will assume x is not 0, right? Then you will lose your solution. So the idea is we move everything to the one side, then factorize it. So you have x equals 0 and x equals 3 over 2. So actually for this equation, you will have two solutions, x equals 0 and x equals 3 over 2. So now let's look at a very special exponential function. Exponential function. A very special exponential function, which is the base is e. What is e? E is actually approximately equal to 2.718 and so on. Okay, so why we are interested? Because this e is a very special number. So where is this e from? Is e from? Okay, and let's look at this. We use another color. Okay, where is e from? Let's look at this one. 1 plus 1 over n to the n. If n equals 1, it's equal to 1 plus 1 over 1, which is equal to 2. When n equals 2, then it's equal to 1 plus 1 half squared, which is equal to about 2 point, oh sorry, yeah. Let's give more numbers, okay. Not 2. Let's look at when n equals 10. So this is 1 over 1 over 10 to the 10th power. So this one is about 2.59374 and so on. Okay, and when n equals 100, then it would be 1 over 100 to the power 100. So this is 1.70481 and so on. Then you continue this way when n is larger and larger. Okay, when n is larger and larger, then this number, when n becomes larger and larger, this number will approach a number which is about 2.18 and something. So we denote, mathematicians say, okay, so this number is so special, which is when n is large, very large, for this special number, it will approach this 2.18, 2.718, about 2.718. And let's denote this 2.718 is a special number which is called e. Okay. So now, our special exponential function is actually this one, f of x equals e to the x. So remember, e is a 2.718, which is greater than 1, right? So the graph would be this one. It still goes through the point, 0, 1 point. Okay? And it's still increasing. It's always be increasing function. And the domain is from negative infinity to infinity. Range is from 0 to positive infinity, right? The y-intercept is still the same, which is 0, 1. There's no x-intercept. Horizontal asymptote is what? Y equals 0, which is the x-axis, the same as a is greater than 1. Okay, so since this is a special case for this function, where f of x equals a to the x, here a is equal to e, right? This is a special function. And the properties still the same, right? We have the same properties, which is e to the x times e to the y is equal to e to the x plus y. E to the x then to the y is actually equal to e to the x times y. E to the x divided by e to the y is equal to e to the x minus y. If you have e to the x equals e to the y, it implies that x must be equal to y.